Today we're going to talk about aromatic compounds. Benzene is an example of an aromatic compound. So if we take a look at benzene, some of the characteristics it has, we're going to have a better understanding of what all aromatic compounds have in common. So what makes benzene special? Benzene is a six-membered ring with alternating pi bonds. It has 3 pi bonds in there. And what makes benzene special is it has some resonance here where we can shift those pi bonds around, 2, 4, 6 electrons all moving around, delocalizing, and we can draw benzene with the double bonds as shown here where the vertical bond is on the left, or like we've done here where the vertical bond is on the right. So these 2 resonance forms for benzene, remember resonance means that neither of these structures really accurately represents what benzene looks like, and in fact the true structure is some kind of blend of those discrete Lewis structures. So sometimes we draw benzene like this. It's represented just with a circle inside of the hexagon. And anytime we see this, you might see this notation a lot when we're looking at other aromatic compounds as well. Anytime you see this circle, it means you have alternating pi bonds. So here we have a 6-membered ring. You're going to put as many alternating pi bonds, conjugated pi bonds as possible. So in this case, we could fit 1, 2, 3 pi bonds. If you look at a 3D sketch of benzene, you know that each pi bond comes from the overlap of p orbitals. So we can show one Lewis structure like this, where we have one pi bond here, and another pi bond here, and another pi bond here. But then if we take a look at the second Lewis structure, I've kind of tipped it over on its side so it's a little easier to see. We still have our p orbital on every carbon. But now the pi bonds have shifted to be between these 2 p orbitals and these 2 p orbitals and these 2 p orbitals. And again, thinking, recognizing that the actual structure is a blend of these, what that really means is we have these 6 pi electrons are actually completely delocalized throughout all of the p orbitals. So what you can draw, and that's what's nice about this structure that kind of looks like a hex nut, what's nice about that ring representation is it illustrates that in an aromatic compound like benzene, we have a cloud of electron density above and below the plane. This is a cloud of electron density above and below the plane. So benzene is a planar molecule, and we have a cloud of electrons above and below. So there's a few nice models that I'd like to share with you that illustrate this very nicely. This is a model that shows benzene, the 6 black atoms here, the carbon atoms, the sigma bonds are in gray, and so you can see that there's 1 hydrogen on every single benzene, and they're all 6 hydrogens and 6 carbons are all in one plane. And what this is showing is there's a p orbital on every single carbon. These are all sp2 hybridized, so there's a p orbital on every carbon. And what's nice about this model is it shows that those pi electrons are really delocalized above and below the plane. Rather than having discrete double bonds and single bonds and double bonds, really benzene has a cloud of electron density above and below like this. Okay, another model that's a lot of fun, but kind of huge, is this one. And this shows, again, same thing. This blue, each blue and green pair represents a p orbital. Remember, a lot of times we color them differently because they have different mathematical signs. And so on every single carbon, we have a p orbital. We also have a hydrogen pointing straight out. That's coming, that's in the plane of the molecule. And when we have this kind of space-filling model of what a p orbital looks like, you can really see how the p orbital on each adjacent carbon is touching and overlapping and interacting and sharing its electrons. So even though we can, maybe think of this as 3 double bonds, really there is no distinction between a double bond and a single bond here because those electrons are equally distributed throughout the plane. So let's list some of the features that we've seen so far. It is a planar molecule. All of the carbons are sp2. They're all sp2 hybridized. That means trigonal planar with that p orbital on each atom. It's completely symmetrical. In other words, all carbon-carbon bonds are equal in length. So again, that's why this drawing is nice, because this shows the symmetry of the benzene, where when we draw benzene, it kind of looks like we have some double bonds and some single bonds, but we don't really. All of these carbon-carbon bonds are equal in length, and the length is about the same as 1.5 bonds. So it's shorter than a single bond, but it's a little longer than a double bond, because that hybrid character has some double bond character, but also some single bond character. Okay, because of this resonance, because we have two resonance forms that equally contribute, that's the best stabilization we can have. So it's very stable because of that resonance. And as a result, we find that even though benzene has pi bonds, it does not react as an alkene. We've seen reactions of alkenes and things that carbon-carbon double bonds will do. Benzene and its fellow aromatic compounds do not undergo the same sorts of reactions. So we'll be studying those in the next lesson. And in fact, benzene then describes a different class of compounds, something called aromatic. And we can abbreviate aromatic with an AR. Anytime you see AR, it means you have something like benzene. Another word that you should be familiar with is called aliphatic. Aliphatic is kind of the opposite of aromatic. Aliphatic is what we have when we have just an R group, like an alkyl group. Aromatic means we have a ring like benzene. So one question we can ask is just how stable is benzene? We know it has some resonance stabilization, but how much does it have? Well, we can use some empirical data. We can measure the heat of hydrogenation, the energy that's released when we hydrogenate the pi bonds on a benzene ring, and see how that compares to the amount of energy we're expecting. So for example, if you had just a single double bond in a ring, you had cyclohexene, and you did a catalytic hydrogenation, that breaks the pi bond, adds a hydrogen to each carbon, right? So you'd get cyclohexane as the product. The heat of hydrogenation for that reaction in kcals per mole is minus 28.6. So let's imagine if we had a theoretical molecule, the theoretical molecule cyclohexatriene. If we put 3 double bonds in a 6-membered ring, but we didn't allow them to interact. So we had a double bond and then a single bond and then a double bond. If somehow we got rid of that interaction and ignored the fact that they were conjugated, and we did a catalytic hydrogenation of this would give the same product. It would still give cyclohexane, and we can predict how much energy we would expect to get in that reaction. Each pi bond is worth minus 28.6, and we have 3 pi bonds, so we would expect to get out 85.8 kcals per mole when we hydrogenated this molecule. So then when we go to do the experiment, of course, the molecule that has 3 double bonds in a ring is called benzene. If we take benzene and we do a catalytic hydrogenation, suddenly we find there's no reaction. It doesn't, remember we just said it doesn't react like an ordinary alkene. So this is a difficult reaction to do. But if you add some heat and you add pressure, okay, if you really pound on it, you can in fact hydrogenate benzene to give cyclohexane as a product. And when we measure the heat of hydrogenation in this reaction, we get only 49.8 kcals per mole. So we're not getting as much energy out as we expected. This is what indicates just how stable benzene is. Let's take a look at an energy diagram to try and make some sense of these numbers. Okay, what we're imagining is that we have cyclohexatriene, theoretically would be producing 85.8 kcals of energy when it gets hydrogenated down to cyclohexane. But benzene, the molecule, actually, the experimental data actually only released 49.8. So we have a difference. We have 36 kcals per mole. Benzene is 36 kcals per mole more stable than we anticipated. We call this the resonance energy. So because it gave less energy off when it was hydrogenated, that means it must have started out at a lower energy initially. And so we can actually quantify it. That's a huge amount of energy. So there's significant resonance going on in this molecule. So let's talk then about the idea of being aromatic and having aromaticity in general, benzene is an example of an aromatic molecule, but it's not the only one. Okay, and there's going to be certain rules that we have to satisfy in order for a species to be aromatic. Now remember, this is the picture of benzene, where we have these clouds of electrons above and below the plane. Turns out that this picture is characteristic of aromatic compounds. So any compound that has this situation, or any aromatic compound, is going to look like this. So how do we get there? Well, first of all, it must be a cyclic molecule like benzene. It has to be a ring, and it has to be planar. Okay, so we're going to be looking at flat molecules like benzene, and we must have contiguous p orbitals. Just like benzene, we need to have a p orbital on every single atom. Okay, now how do we get a planar molecule that has a p orbital? Typically, we're looking at an sp2 hybridized atom. They can't be sp3 because sp3 hybridized atoms don't have any p orbitals. You have to have a p orbital. Contiguous means continuous. Every single atom has to have a p orbital. Okay, and finally, we have to satisfy something known as Huckel's rule. In Huckel's rule, it says that the number of electrons that are in those p orbitals must be a certain number. They can be either, you can have 2 electrons, or 6, or 10, or 14, or 18, and so on. You have to have a specific number of electrons. Now, rather than memorize this never-ending list of numbers, what was determined by Huckel is that these all fit the 4n plus 2 formula. So sometimes Huckel's rule is known as the 4n plus 2 rule. And this is where n equals any integer, 1, 2, 0, 1, 2, 3, etc., any integer. So rather than memorize this list of numbers, all we have to remember is 4n plus 2. And then we can see that if n is 0, then that would come out 2. 2 is one of these magic numbers. If n was 1, we'd get 4 plus 2. 6 is a magic number. 8 plus 2, 10, and so on. So this is a way that we can look at a huge, a very large number and quickly determine whether or not it fits this formula. So let's take a look at benzene. We said benzene is an example of an aromatic compound. Let's make sure it satisfies all the rules. Okay, it's definitely cyclic and planar. We saw that with our model. They're all sp2 hybridized, so we have a p orbital on every single atom. That's good. And then let's check the number of electrons. How many electrons does benzene have in those p orbitals? We're trying to see how many electrons are delocalized in that pi system. Well, we have 3 pi bonds. Each has 2 electrons. 2, 4, 6. We have 6 electrons. And is 6 one of our magic numbers? Yep, that fits 4n plus 2. If you know benzene is aromatic, then that number 6 will always, should always be something that you automatically know is a good number that fits Huckel's rule, fits the 4n plus 2 rule. Yes, benzene is an aromatic compound. So let's take a look at some other compounds and see whether or not they're aromatic. Okay, pyridine is an example of an aromatic compound, and it looks just like benzene, except we have a nitrogen in the place of one of the carbon atoms. Okay, so yeah, I see that it's cyclic and planar. Okay, every atom is sp2 hybridized. That's good. It has a p orbital on every atom, so that's good. But when I look at the electrons, I see 2, 4, 6, 8. So I have 8 electrons. Is that one of our magic numbers? Does 8 ever fit 4n plus 2? No, 8 fits the formula 4n. Anything that's a multiple of 4 can't be one of can't be something that would be aromatic. Okay, yet pyridine is an aromatic compound, so we're making a mistake somewhere. So the mistake we're making is that we're not counting up all the electrons that we see. We're counting up only the electrons that are in the p orbitals, that are part of this system. This lone pair is not in a p orbital because this nitrogen already has a pi bond occupying that p orbital. This lone pair is in the sp2 plane. It's in an sp2 hybrid orbital. So if we imagine this as a model of pyridine instead of benzene, this would be a nitrogen, and instead of having a hydrogen here in the plane, it would be a lone pair of electrons. And so we wouldn't include these two electrons as part of these electrons because they're in different regions of space. So we ignore these in our electron count. Okay, and let's make a sketch of pyridine so we can have a record of that. Okay, what I'm saying here is that there is a hydrogen on every carbon that's in the plane, and there is a lone pair on this nitrogen that is in the plane. In addition, we have a p orbital on every atom, as we need to, and we have 2, 4, 6 electrons in those p orbitals. This is just one of the Lewis structures we can have for pyridine, because we know we can have resonance showing another one. Okay, so these two electrons are not in the p orbitals, so we don't count it. We don't include that. We don't count them. We don't include that in our electron count. So Huckel's rule is going to involve making sure we know which electrons we're including to see if we fit our 4n+2 rule. How about furan? Now again, we have 2, 4, 6, 8 electrons that are possible, that we see, but we need to figure out whether or not we can count those, whether or not we should count all those electrons. The key to understanding furan is considering what is the hybridization of that oxygen. What is the hybridization of that oxygen? It could be sp3. Normally, we would say that an oxygen, 2 bonds, 2 lone pairs, 4 regions of electron density, we would say it's going to be tetrahedral. It's going to be sp3 hybridized. But remember, anytime a lone pair is allylic, anytime it is next to a pi bond, and it can have resonance, like we can show this, that means that lone pair must be in a p orbital. So it's not going to be sp3 hybridized. It's going to be sp2 hybridized. One of these lone pairs is in the p orbital, and the other lone pair is in the sp2 hybrid orbital. So how many electrons, how many lone pairs do we count for our Huckel's rule? We only count 2 of the 4, so we have 2, 4, 6. We end up with our magic 6 electrons for Huckel's rule. And we also needed to be sp2 hybridized for this oxygen because we had to have a p orbital. That's the only way we could have a p orbital on every single one of these atoms. So again, let's take a look at our sketch. If it was sp3, let's compare these two. If it was sp3, that means we have a pi bond here and a pi bond here, and then this oxygen would be tetrahedral, right? So we have 2 bonds in the plane, and then 2 other regions of electron density are a wedge and dash above and below. We could just kind of put our electrons out there to show spatially where they are. Okay, this is unfavorable because there's no interaction of the lone pairs with the pi bonds. There's no delocalization. And remember, electrons like to spread out as much as they can. Delocalizing is a good thing. So instead of this, being sp3 hybridized, it's going to prefer to be sp2 hybridized. And if it's sp2 hybridized, then that puts a p orbital on the oxygen. So now we can become aromatic because we're cyclic and planar and we have contiguous p orbitals. And we're going to have a pi bond here and a pi bond here, and we're going to put our lone pair of electrons in that 5th p orbital. So now we have 2, 4, 6 electrons delocalized in the pi system. Perfect, aromatic. Where's the second set of electrons? Just like in pyridine, it's going to be part of the plane of the furan molecule, and so we don't count these. We don't count these, and we do count these. So that's what furan looks like, an example of an aromatic compound. Related to furan, if we had a sulfur in this in the 5-membered ring, that molecule is called thiophene. This is also an aromatic molecule. And in order to do that, again, we would have to make this sp2 hybridized. So this is in the sp2 plane, or one of them, doesn't matter which. And one is in the p orbital and one is in the sp2. So analogous to furan, the sketch would look identical. This has 6 pi electrons now, 2, 4, 6 electrons in the p orbitals. Pyrrole is another 5-membered ring that is an aromatic compound. Do you think we should include those 2 electrons in our electron count? I think, yeah, we're going to make this sp2 hybridized once again. So this hydrogen is in the plane with all the other hydrogens. And then what do we have in the p orbitals? We have this lone pair and this pi bond and this pi bond. 2, 4, 6 electrons. Pyrrole is also an aromatic compound. These ones with hetero atoms in there, something other than carbon, we call these heteroaromatic compounds. Thiophene, pyrrole, and pyridine, furan, those are all examples of heteroaromatic compounds, and those are all names that you should be familiar with. An aromatic compound can be a charged species. Let's take a look at this one. We have a carbon with a negative charge. Now, what does it mean to have a carbon with a negative charge? Let's complete this Lewis structure so that we have a good understanding. If we're going to be counting up electrons, we need to know how many electrons we have. So in order for a carbon to have a negative charge, that means it has 5 electrons for its electron count. It's going to have 2 bonds, it's going to have a 3rd bond, and a lone pair of electrons. That's what a carbanion looks like. It needs 3 bonds and a lone pair. So we have 1, 2, 3, 4, 5. Carbon only wants 4, so that's how we end up with a carbanion. Okay, so when I draw out that structure, this now looks an awful lot like the pyrrole we just saw, right? With 3 bonds and a lone pair here. And we would expect this carbon, just like just like pyrrole, to have sp2 hybridization here. It has to be sp2 hybridized if we want to delocalize that charge and move the negative charge around, which we can do here. And actually, we can continue doing resonance, and we can move it around to another position. And we can keep going, etc. In fact, as a matter of fact, this this negative charge can be delocalized over all 5 atoms of the 5-membered ring. So is this an aromatic compound? It's cyclic, it's planar, we have a p orbital on every atom, and we have 2, 4, 6 electrons. It is an aromatic compound. An abbreviation for this molecule that is very common to see is to draw that circle in the middle and a negative charge. To say that over these 5 rings we have alternating pi bonds, as many alternating pi bonds as we can have. How many can you fit in a 5-membered ring? You can only fit 2 alternating pi bonds, conjugated pi bonds, and overall the molecule has a negative charge. This is a very stable anion because it's aromatic. It doesn't just have resonance, it has aromatic resonance. And this is called the cyclopentadienyl anion. The cyclopentadienyl anion is a fairly easy anion to make, even though it's a carbanion. This is a very, very stable negative charge. And let's take a look at a carbocation example. Again, what does a carbon look like? What are the details of that carbon if it has a positive charge, if it's a carbocation? How many bonds, how many lone pairs? Now we need to have an electron count of 3. We need to be missing an electron. So all we have here is a single bond, so it must be a hydrogen there. So now we have 1, 2, 3 bonds. Carbon wants 4, so it's missing 1. That's what a carbocation looks like. So a carbocation, remember, is sp2 hybridized. It only has 3 regions of electron density, so we've seen that before as being sp2 hybridized. So it has that p orbital. What's in the p orbital? There's nothing in the p orbital. It has an empty p orbital, but that's fine because all we need is to have a p orbital. So we now have a ring. It's planar. It has a p orbital on every single atom. And how many electrons does it have in that pi system? Let's count them up. 2, 4, 6. 6 electrons that looks like it's going to be extremely stable. It is, in fact, aromatic. And as you can imagine, because this is an allylic carbocation, we can move this positive charge around. Sorry, I put my pi bond in the wrong spot. 7-membered rings always look a little strange. Now it's still allylic. We'll just say etc. In fact, in this case as well, you can relocate that positive charge onto all 7 carbons. So the way we draw this charge species is we draw a 7-membered ring with a circle in the middle and a plus charge. Again, a pretty famous carbocation, pretty commonly known because it is aromatic. And what is this guy called? It's a 7-membered ring, so that's a cycloheptane, but it has 1, 2, 3 pi bonds. So this is called the cycloheptatrienyl cation. So the cycloheptatrienyl cation is also a extremely stable carbocation. So we can have charged aromatics as well. And this is an example. This is called naphthalene. This molecule has 2 benzene rings fused together. This is described as a fused aromatic system. And if benzene is aromatic, then when you stick 2 benzene rings together, you will still have an aromatic system. And what let's check to make sure it follows all of our aromaticity rules. We have a cyclic system. Here's our ring on the outside here. We have a p orbital on every atom, pi bond to every atom, so there's a p orbital there. They're all sp2 hybridized. And how many electrons do we have total? 2, 4, 6, 8, 10. We have 10 electrons. So this is our first one where it's not a 6-electron system, but is this still one of our magic numbers? Well, this is where it comes in handy to remember 4n plus 2. It's the 4n plus 2 rule. So is there any number for n that you can come up with? Doesn't matter what n is, but is there any way to make this formula come out to 10? Sure, if you make n 1, if you make n 2, then this is 8 plus 2, and this would be 10. So yes, it is one of the magic numbers that satisfy Huckel's rule. So naphthalene and any fused aromatic system, fused benzene ring system, is going to be aromatic as well. So let's test it out on a few examples here. Let's see if we can figure out whether these are aromatic or not. Here we have a cyclic system. We have 2 electrons. Is 2 electrons one of our magic numbers? Well, let's come back again to 4n plus 2. Is there any way you can make that formula equal 2? If n is 0, which is an allowed integer, if n is 0, then that number disappears and it becomes 2. So yes, 2 is an okay number, but is it aromatic? It's cyclic. The 3 carbons are in a plane. They have to be. Do we have a p orbital on every atom, though? P orbital, yes. P orbital, no. What is this? What is the hybridization of this carbon? Let's draw out our line drawing. This is actually a CH2 group. This is sp3 hybridized. And there's nothing you could do about that. You can't make it sp2. You can't put a sigma bond up in a p orbital. A lone pair you can put in a p orbital. But if you have 4 sigma bonds, 4 single bonds, you have no choice. It must be sp3 hybridized. So this is not aromatic. This is not aromatic. Because every single one of the rules has to be satisfied in order to be an aromatic compound. How about this one? We have a positive charge now on that carbon. Does that change anything? It absolutely does. That now we just have 3 bonds. And so this is now sp2 hybridized. That gives us a p orbital on this carbon. Now we have a p orbital, p orbital, p orbital. And those 2 electrons can now delocalize. Those 2 electrons are the right number. And yes, it is aromatic. Okay, what you need is you have to have a p orbital on every single atom to provide the avenue through which your electrons can delocalize. You have to complete that circuit in order to be aromatic. So actually, this is a pretty famous carbocation. We can abbreviate it like this. This is known as the cyclopropenyl cation. And we draw that circle. Remember, that circle means that you have alternating pi bonds, but for a three-membered ring, you can only fit in one pi bond. So there's one pi bond and there's a positive charge on the carbon that doesn't have a pi bond. So cyclopropenyl cation is aromatic. How about this next one? It's planar. We have p orbitals. We have 2 electrons. Everything's good. Well, what's the problem? It's not cyclic. It's not cyclic. So no, it is not aromatic. It's resonance stabilized. It's the allyl carbocation. It's a very stable carbocation. It's a good carbocation, but it doesn't have that extra special resonance stabilization that we define as being aromatic. So you have to have those atoms all in a ring in order to be an aromatic molecule. Okay, let's try this one. This is cyclooctatetraene, has 8 carbons and 4 double bonds. Cyclooctatetraene is cyclic, and it could be planar. You can't, just like a stop sign, you can put that in a plane. And how many? It has a p orbital in every atom, certainly. How many electrons are there? 2, 4, 6, 8. We have 8 electrons. Is that 4n plus 2? Is that one of our magic numbers? It is not. It is 4n. And actually, if you have all the ingredients of aromaticity, cyclic and p orbitals, and you put in the wrong number of electrons, you put in 4n instead of 4n plus 2, you actually get a system described as anti-aromatic. That's especially unstable because you're trying to force the wrong number of electrons into this delocalized system. So what happens is, rather than be anti-aromatic, it's going to bend. So it's not going to want to be planar. This molecule actually bends so that the pi bonds cannot interact with each other. Each of these pi bonds is not in the same plane as the other pi bond, so there's no interaction, there's no resonance whatsoever. And this is a more stable form than trying to delocalize the electrons but put them in a something that violates Huckel's rule. So this is a kind of a boat-shaped molecule like this instead. Okay, so we've pointed out how important this 4n plus 2 rule is, but what makes that so special? Why is it that a molecule, that system with 6 electrons is fantastic, but 8 electrons, it's horrible? What is the background for that? And I'd like to just go into a little bit of molecular orbital theory, MO theory, to explain where this aromaticity stability comes from. Okay, so let's review what a pi bond looks like. You form a pi bond. A pi bond is described as a molecular orbital, an MO, by overlapping p orbitals. And p orbitals are atomic orbitals. Okay, you bring those 2 p orbitals together to form a pi bond. But when they combine, when these 2 p orbitals combine, there's 2 ways that they can combine. We're actually combining them mathematically. They can either combine it in this way, or we can flip it over and combine it that way. So it's like you're adding them or subtracting them. So if we describe this as PA and PB, let's say they have the same phase. And again, we're using some shading here to indicate the mathematical signs. So let's assume the signs are the same on the top lobes and the same on the bottom lobes. So if you add these two together, PA plus PB, you're going to have a positive interaction with the top half and a positive interaction with the bottom half. So your new molecular orbital is going to look like this, where you have a large lobe on the bottom and a large lobe on the top. We describe this as a bonding molecular orbital. And we call this bonding molecular orbital a pi molecular orbital. And that's exactly what a pi bond looks like, right? We have a cloud of electron density above and below. Okay, but that's not the only possible combination. If you subtract these two so that the phases don't match up, we describe them as being out of phase, we get this as our molecular orbital. This is described as an anti-bonding. And we call it a pi star. The asterisk indicates that it's an anti-bonding type of orbital. And we're drawing it like this. We're drawing this one higher because this is higher in energy. And what we can see in this picture of the molecular orbital is that we have nodes, and we have a node here too. Anytime you change the mathematical sign from one to the other, we describe that as passing through a node. A node is where you have a zero probability of finding an electron. So remember, these molecular orbitals define an area of probability of where the electrons are most likely to be. So if you have a pi electron, it's going to most likely be in a cloud above the atoms or a cloud below the atoms, but has a zero probability of being right between the two nuclei. Okay, and the antibonding has this node, but it has another node, so that has even more. And what we see is that as you increase the number of nodes, you increase your energy. It becomes higher in energy, it becomes less stable. So, and this, we call it antibonding because there's no positive interaction between these. There's nothing, if you had electrons in here, that's not something that would bring these nuclei together and hold them together in a bond. So this is the difference between bonding and antibonding. And so now let's look at the electrons. If we think of the p orbital of one carbon atom, let's say, coming in with one electron, and the other p orbital has an electron, we bring those together to form a bond with two electrons. Where are those two electrons going to go? The new possible homes that they have, the new molecular orbitals, are the pi and the pi star. Well, they're going to pair up, and as usual, they're going to fill in the lowest energy orbital, the most stable orbital first. So we put them down here, and that's what our pi bond looks like. So we have two electrons fill the more stable molecular orbital, and that's what we describe as a pi bond. We have two electrons in a pi molecular orbital. Okay, so that's the simplest system when we have just a single pi bond. Now let's take a look at benzene. Benzene doesn't have just a single pi bond. It has 3 pi bonds involving a total of 6 p orbitals. And because these are all interacting and involved in resonance and delocalizing the electrons, all 6 of those p orbitals are going to be combined to form new molecular orbitals. And so if you have 6 p orbitals, you're going to get 6 new molecular orbitals. And we're going to observe that same shift, that once you do your combination, half of them are going to be favorable interactions, the other half are going to be unfavorable. So these 6 new molecular orbitals will have 3 that are bonding orbitals, so we call them pi, and 3 that are anti-bonding. That we'll describe as pi star. And what I've shown here is an energy diagram. This is called an MO diagram for benzene. We have 3 lower energy orbitals called pi. So down here we have all of our bonding orbitals, low energy stable. And then up here we have 3 anti-bonding, all high energy. And this line in the middle, we call this the non-bonding line. Sometimes we have orbitals right at this level. This is kind of halfway between the energies. And in these orbitals, we have an equal number of bonding interactions and non-bonding interactions. Okay, so what we haven't shown here is what each of these pi molecular orbitals look like. Okay, well, let's think about this lowest energy one, the most stable one. Let's imagine shading each of these p orbitals mathematically. What would be the best possible interaction that you can have between those p orbitals? Well, clearly, if they were all in phase, so in other words, let's draw that right here. If we had our 6 p orbitals, and for every one of them the top half was shaded in, that would be the most stable. It has it has just the one node of the plane, has no additional nodes. This is going to be the most stable we can have. That's going to be the lowest energy, and that's exactly what it is. All of the interactions between adjacent p orbitals are bonding interactions, favorable interactions. Okay? That's one possible combination. Another combination would be if you now introduce a node. where half are, half are one side and half are the other side. That's going to be higher in energy, and so that's what these look like. I'm not going to draw them all. Then we have a couple nodes, and we're even higher in energy still. What do you think this worst one looks like? What would be the worst possible interaction between these p orbitals so that there's no bonding interactions whatsoever? It's completely anti-bonding. Well, again, that extreme is pretty easy to imagine. What if we had alternating signs? So we shade in the top half, and then the bottom half, and then the top half, and the bottom half. If we did this, then there's not a single bonding interaction between any of them. It's completely anti-bonding, and we have a node and a node and a node. We have tons of nodes, and so that's the highest energy. So something that would be on this non-bonding line would have just as many, would have some bonding interactions, but just as many anti-bonding interactions. So it kind of cancels out. It's neither bonding nor anti-bonding. It's somewhere in between. Okay, now this is benzene. How many electrons does benzene have in those p orbitals? How many electrons do we have to fill into this diagram? We have 2, 4, 6 electrons. So these are the molecular orbitals into which we can fill with the electrons and place the electrons. Where are we going to put them? Well, as usual, we'll start with our lowest energy orbital and fill it in. There's 2 electrons, and then we move up to the next higher energy. We could put 2 electrons here, and we could put 2 electrons here. And what do we have? We've used our 2, 4, 6 electrons, and what we end up with is an MO diagram that looks extremely stable, looks really, really good. What we have here with these 6 electrons is we have completely filled bonding molecular orbitals. So all of our pi molecular orbitals are completely filled. We have no electrons up here in the anti-bonding, and we have all paired up electrons down here. This is going to happen every time we have 4n plus 2 electrons, and that's what's so magical about that number and so stable for to satisfy Huckel's rule. So this is what benzene looks like. Let's take a look at some other size rings, see if we can come up with their MO diagrams. And what I want to point out is they're going to have some things in common with this. Okay, there will always be one MO with the lowest energy. Okay, there's always just one instance, one arrangement where they're all in phase. That's going to be the lowest point in your MO diagram. You'll always have one down there. Okay, after that point, your MOs are always going to occur in pairs. Okay, so then we have pairs of degenerate. We call it degenerate when they have equal energy. Pairs of degenerate MOs. So we start with one lowest, and then we go in pairs, and then we go in pairs. And how many will we have total? How many will we have total? Well, however many atomic orbitals went in is how many molecular orbitals come out. Okay, so let's take a look at some examples. And actually, we can point this out in benzene. There's something called a polygon rule, or something that helps you see what the MO diagram should look like. If you look at this MO diagram and you connect your MOs, you end up drawing the shape of the molecule. So benzene is a 6-membered ring. You can draw this polygon on its point. You can see the hexagon in there. Okay, and that's because if it's a 6-membered ring and every atom has a p orbital, then you have that same number of p orbitals and you'll have that same number of MOs. So you'll always have the same number of points here that you had in your original system. Okay, so let's see if we can try some new ones. Okay, how about a 3-membered ring? And I pointed out in the beginning here, the number of the MOs is going to be equal to the number of atomic orbitals, which is always equal to the number of atoms in the ring. So we're going to look for that polygon to give us the shape. So a 3-membered ring, like this is an example here. A three-membered ring should have 3 MOs. Now I've drawn the non-bonding line here because it's kind of tricky to know what to do with 3 of them. It turns out that we have one that's low energy that's bonding. So we label that as a pi, and then we have 2 that are anti-bonding. That's what a 3-membered ring looks like. We're increasing in energy as we go here. So we have 1 pi and 2 pi stars. And let's take a look at this example. Let's fill in the MO diagram for this molecule. How many electrons does this have in the p orbitals? It has just 2 electrons, so we put those down in the lowest energy, and then we're done filling in our electrons. Now, looking at this MO diagram, would you say this looks like an aromatic system? It has just 1 bonding orbital that is full, therefore it's aromatic. Because we have, just like benzene, we have filled bonding molecular orbitals. So that's why 2 is a magic number in cases like a 3-membered ring, because all you need is 2 to fill in all of the bonding orbitals. Okay, how about a 4-membered ring? This is, we have 4 atoms, so there must be 4 MOs. Okay, and we have these should not be labeled pi. These are non-bonding. Sorry, we have a pi and a pi star, and then these are non-bonding. And now we have 2 of them are going to be right in the middle on the non-bonding line. One is going to be lowest energy. One is going to be highest energy. I forgot to put on our polygon here. You can see our 3-membered ring. Here you can see our 4-membered ring. Right? So we start with 1, and then we draw a pair of degenerate. And then we go back to just 1 because we only had 4 total. So 1, 2, 3, 4. Now let's fill in our electrons. We have 4 electrons to add in. So where would those 4 electrons go? We would put 2 down here in our lowest. And then we have 2 more electrons. So how do we fill those in? Well, we fill 1 in each degenerate electron. Remember, we don't pair them up until they're spread out into 1 in each orbital of the same energy. And so does this look like an aromatic system? Does this look like a very stable system? No, it's got unpaired electrons. This is not aromatic. This is not stable. Okay, so we knew that because it was 4 electrons. 4 n plus, that does not fit. This is not 4 n plus 2. So we can predict it just looking at the molecule and going through our aromaticity rules. But what I want to point out is by inspecting the MO diagram is how we can prove why this is an unstable system and verify our predictions. Okay, let's see if we can draw some others. How about a 5-membered ring? If we have a 5-membered ring, how do we draw that? We start with 1 in the lowest energy. There will always be a pi molecular orbital at the lowest energy. That's where all the p orbitals are in the same phase. And then we go in pairs. We have 2, and then we have another 2, and how many more? Well, it's a 5-membered ring, so we're going to get 5 MOs, so we're done. We have 1, 2, 3, 4, 5. Now with a 5-membered ring, it's a little tricky to know where the non-bonding line is, but it turns out it's right above this. So these 3 are pi molecular orbitals, and these 2 are pi star. It's not completely symmetrical, so you have to know where to put that line. And so let's take a look at furan. Furan, we said, was an aromatic molecule. Let's see how its MO diagram looks like. How many electrons should I put in here? I've drawn my polygon. I have my 5 MOs. So this is a good MO diagram for furan, a 5-membered ring. How many electrons? 2, 4, 6. This has 6 electrons. Remember, we're just counting one of these because they're in the p orbital. And the other pair is in an sp2 orbital, so we don't count those. So we have 2, 4, 6 electrons. Where do we put them? 2, 4, 6. So just like benzene, it has 3 bonding molecular orbitals, so 6 is something that imparts aromatic stabilization. Okay, and finally, how about an 8-membered ring? An 8-membered ring, we start at the bottom with 1, and then we go in pairs. There's 3, 4, 5, 6, 7, 8. So there's our 8 total. And because it is a symmetrical number of things, we can draw a non-bonding line right in the middle. So these are clearly going to be pi's. These are going to be our bonding electrons. And these are going to be pi star, non-bonding electrons. And here's an example of an 8-membered system. We have 2, 4, 6, 8, 10 electrons. We have 2, 4, 6, 8, 10 electrons. Is that a magic number? 4n plus 2 is a magic number. So we're expecting this to be a good structure, so let's fill it in. We have 2, 4, 6, and then 8, and then 10. We've filled in the all 10 electrons are in bonding molecular orbitals. We don't have any electrons in the antibonding. We don't have any electrons that are unpaired. And so this is another stable system. Okay, so the MO theory is there to back up what we're predicting with our simple aromaticity rules. And finally, let's look at some examples where we can use aromaticity. Now that we know that aromatic compounds exist, that can explain some things we have about reactivity. And what we're going to do is we're going to look for aromaticity as kind of the ultimate in resonance stabilization. We've seen so many examples where resonance was key to explaining why something's so stable, why something reacts the way it does. And so resonance now is just another big example of that. So here's a question. We compare these two molecules and we ask, which is more acidic? Which is more acidic? How do you ever answer that question? What does it mean to be an acid? It means you donate a proton. So we're asking which of these is more willing to give up a proton. And the way you answer that question is you let each of them donate a proton, you let each of them act as an acid, and you look at the conjugate base. You look at the conjugate base. In other words, let's imagine a base come in here and grab a proton from each of these. What does the base look like? What does the conjugate base look like? You now have a lone pair and a negative charge where you used to have that proton. So we have this anion. Here we have a 7-membered ring. I don't know if I drew a 7-membered ring there. 2, 4, 6. Pi bonds. So we have a 7-membered ring. We have this anion, this anion. So we compare conjugate bases, and then we ask which one is more stable. Well, each of them is allylic. This has resonance, so I can delocalize my negative charge down here, and so on. Okay, and this has resonance, where I can move this around. I think I moved it a little extra. I can move this negative charge around and continue, and etc. So based on what we've seen in the past for resonance, what would be your prediction? Which one of these do you think has more resonance? Well, it looks, because this has just the 2 pi bonds, it looks like this is going to have less resonance than the one with 3 pi bonds, because we're going to be able to use all these pi bonds and move it around. Okay, so, we're at first glance, we're wondering, does this have more resonance? Is this more stable? Well, that would be a possible conclusion before you knew about resonance, aromatic resonance. Now that we know about aromaticity, as soon as you see a cyclic system with pi bonds and p orbitals, you need to consider aromatic requirements. Okay, so let's look at this in terms of aromaticity. How would you describe this first conjugate base? Is it aromatic? Because it is cyclic, planar, it does have the p orbitals, it has 2, 4, 6 electrons. This is aromatic. And how about this one? It's cyclic, it's planar, it has 2, 4, 6, 8 electrons. Is that 4n plus 2? That is not. This is anti-aromatic. So this resonance is not true. It's not possible for those electrons to delocalize throughout all those pi bonds, because in order to do so, it would force it to be planar, and then we would have one of those unfortunate looking MO diagrams that we had on the previous slide. Okay, so and what this molecule does then is it bends so that it disrupts that resonance, and so it does not have all the resonance stabilization that we're expecting. This is anti-aromatic. Okay, if you didn't know about aromaticity, you would have gotten this problem wrong. So because this is aromatic, this is the more stable and therefore less reactive conjugate base. Less reactive, weaker. We can add that in too. More stable, less reactive, weaker conjugate base. And the weaker conjugate base has the stronger parent acid. Has the stronger parent acid. So which of these two polyenes is the stronger acid? This is more acidic. Okay, because aromaticity is the best resonance we can have. So if we can find that, we know that that beats any other kind of resonance we might have. Okay, let's try another example. Let's look at these two amines, these two nitrogen-containing compounds, I should say, and ask which is more basic. This is pyrrole, this is pyridine. We've seen both of these. They're both aromatic compounds, heteroaromatic compounds. Let's ask which is more basic. What does it mean to be a base? You accept a proton, right? So each of these nitrogens can be a base because they have a lone pair. So we can imagine having it interact with an acid and get protonated. And so what we need to do now is we need to look at the conjugate acids. We know each of these starting materials, these are both aromatic. We know we're starting with stable starting materials. They're both aromatic. So let's look at the conjugate acids and see what they look like. So in other words, we're going to protonate pyrrole. That gives a nitrogen with 4 bonds, so it's positively charged now. 1, 2, 3, 4. Nitrogen wants 5, so it's missing an electron. There's a protonated pyrrole, and here's a protonated pyridine. Okay, we look at these two conjugate acids and we ask the same question. Which of these is more stable? Well, pyridine looks like I still have my benzene ring, right? I'm not my benzene ring, I still have my aromatic ring. It looks like benzene though. It still has the 6-membered ring, it still has the pi bonds. This conjugate acid is still aromatic. How about the protonated pyrrole? We now have, this is now sp3 hybridized, so we've lost our p orbital, so that makes it impossible to be aromatic. We only have 4 electrons, so even if it was still there, we wouldn't have the right number of electrons. And so this has lost aromaticity. Does that sound like a good process? Does that sound like a good reaction? No way, because you're so stable, and if you give up that aromaticity, you lose that stabilization, you go higher in energy. Okay, so because this is still aromatic, this is the more stable, weaker conjugate acid. So it has the stronger parent base. Because this has lost aromaticity, this is the less stable and therefore stronger conjugate acid, and that means it has the weaker parent base. What you could say is you could say that pyrrole's lone pair, why is there a difference here? Because pyrrole's lone pair is part of the aromatic delocalized electrons. Those 2 electrons are needed to have that delocalization, that resonance stabilization. So you could say pyrrole's lone pair is tied up in aromatic resonance. Okay, and by using it, by reacting it with an acid, you're taking it away from the aromatic system, and you're losing that resonance stabilization. Okay, how is that different from pyridine? This lone pair is not part of the aromatic system, so that makes it more available. It's happy to react. It can form a bond with no problem. It doesn't disrupt the aromatic system at all. Remember our sketch of pyridine? We looked at pyridine today. Imagine that one of these being the lone pair, forming a bond here has no impact on these 6 electrons that were in the pi bonds that are part of the pi system, so that makes pyridine a pretty good base. In fact, where have we seen pyridine before? We've heard of pyridine before. We've used it as a base. This is a good base. It's a good organic base that's used when we need such a thing, and so this explains why it's a good base, even though it's an aromatic and stable compound. So this wraps it up for the discussion about what it means to be an aromatic compound and like benzene. And what we'll move into next, the next lesson is going to start looking at the reactions that aromatic compounds can undergo.